this video, we're going to be looking at some implicit differentiation, and then later on we will apply it to some real life problems and do some related rates. So up until this point, we've looked at functions where y equals f of x. That's where y is expressed explicitly in terms of x. You have y on one side by itself equals x is on the other. But not all equations are expressed in this form. Some equations are expressed with y implicitly as a function of x. For instance, the equation of a circle with a radius 4 would be given as x squared plus y squared equals 16. It's always x squared plus y squared equals r squared. So this is a circle with radius 4. And we would want to express this way because then we can tell it's a circle. But if we have to take the derivative of this, we are only used to taking the derivative if it's y equals something. So if we had to make this y equals, well, first of all, we would subtract the x squared over. We would say y squared equals 16 minus x squared, and then we'd end up having to do the square root. And since the right side has a number on it, we'd have to do plus or minus square root. That means we would get two functions we'd have to take the derivative of. We'd have the square root of 16 minus x squared, and then we'd also have negative square root of 16 minus x squared. So that's not as useful. Instead of solving for y every time, we're just going to take the derivative of this implicit equation. So this equation is called implicit. It has x's and y's mixed up together versus these are explicit. Y is explicitly in terms of x. And we are going to do some implicit differentiation to get a single unified derivative. Instead of having to take the derivative twice, once of the positive root and once of the negative root, we can just look at this original function here and take the derivative of that. Not to mention, these would both be chain rules if we had to solve for y, versus this derivative would be a lot simpler. We'd bring down the power, subtract one for the new power. It wouldn't be as complicated as using the chain rule. So we want to learn how to do this. When we have x's and y's on one side, what are we going to do first? First thing we're going to do is we are going to take the derivative It's going to be a normal derivative. Take the derivative using our typical derivative rules, but we're going to put a dy dx next to each derivative of y. If you take the derivative of y, you need to put a dy dx next to it. Derivative of y with respect to x is what that dy dx means. And then our second step is going to be to solve for the derivative by itself. Solve for dy dx. We might have to add or subtract something over and then divide. We're going to get dy dx on one side by itself. So for instance, from our example above, that x squared plus y squared equals 16. If we wanted to find the derivative of that, find dy dx, we would take the derivative of both sides. So starting with the derivative of x squared, we would say the derivative of x squared is 2x. That wasn't a derivative of y, so we don't need to put a dy dx on it. But then the derivative of y squared is 2y. And we'll put a dy dx on that. We took the derivative of y with respect to x equals 0. And now we want to get dy dx on one side by itself, so we'll subtract that 2x over to get just the dy dx on the left. I'm going to bring this up here. So we'll get 2y dy dx equals, we subtracted 2x over. And lastly, to get dy dx on one side by itself, we would need to get rid of this multiplication by dividing by 2y. So dy dx would be negative 2x divided by 2y. And yes, you could simplify this. Those 2's actually cancel out, so you could just say negative x over y, but you don't have to simplify anything. You could also just leave it as that. So it allows us to take a regular derivative, but we do have to get dy dx by itself at the end after taking a normal derivative, where we just put a dy dx next to each derivative of y term.